This week the crystals have gotten larger, although there aren't as many of them or as large as I would anticipate if the solution was larger. The solution hadn't been spilled. But in terms of looking for effective techniques to grow bigger crystals and even just higher quality crystals, our saturated solution technique, which is this slow evaporation technique, is it's good and it's easy to use, but it takes a while, and also you need a lot of the saturated solution, and it's not very good for growing a large crystal by itself. So instead, what you could do is you could use convection. So instead of making the crystal form in the solution, you allow this crystal to form inside of a gradient. So if the temperature gradient is different, then the crystal will move from the cold to the warm, and then that'll allow for a bigger and good high quality crystal to grow. Okay, so moving on to the despacing of the crystal structure, it's relevant to our experiment due to the fact that despacing and the angles between the planes is going to enable us to be able to figure out where all the atoms are in the structure and figure out the 3D crystal structure that we're creating. And so to do this, we're actually going to use Bragg's law, and Bragg's law is up here in the top left. This n lambda equals 2d sine theta, and the basis behind it is that so the x-rays come in all parallel to each other and with the paths that are the same length over here, and then all of them will strike and then be reflected out, and so the x-rays come in and then out, and the angle of incidence, the theta, is going to be the same as the angle of exit, which is this theta. And then the final and lowest path will have this kind of effect from the previous path, where we have this extra distance here represented by this theta and a 90-degree angle, and that's the part that we're actually looking at, and that's the most important part for the analysis. So the final path is going to have this half path length distance right here, and then this is a theta due to this angle being the same as that angle, and then because it's a 90 degree, and then this hypotenuse of the right triangle is going to be the distance between the planes. And so from doing this, we'll be able to determine what our d value is, and then which is what we're looking for. So we do n lambda equals 2d sine theta at where the highest peak of incidence is. So if we look at the data that we were given to analyze, the highest peak of incidence is right here, which is this peak right here, which is about 20.5 is 2 theta degrees, and it's at 1250 counts, I'd say. And so we look at that highest peak, we can find the theta value, which is going to be 10.25. We assume that the n is 1, which is an integer multiple of the wavelength, and the wavelength is given to us at 0.15418 nanometers, which is up here in the top right on the graph. And so from this we plug in our values that we're given, and we get 4.33 times 10 to the negative 10 meters, which is 0.433 nanometers, and that's our that's our separation, so that's our d value, and that's the relevance of that. And from that, we're actually able to know exactly what the d value is and exactly how the spacing is between the planes. Yeah. And this is relevant also to growing the crystals, because if you grow bigger crystals through other methods, such as convection and then liquid-liquid diffusion, you're going to be able to get d values that are different and bigger than this.